For more than 2 million years, the Ice Age belonged to giants. Across vast grasslands and open woodlands, mammoths crossed frozen valleys. Giant ground sloths stood taller than elephants when they reared onto their hind legs. Ancient horses, enormous bison, camels, and herds of creatures with no living equivalent filled a world that no longer exists, and moving among them was a predator unlike any cat before or since. It survived ice ages that reshaped continents. It endured shifts in climate that erased entire ecosystems. It spread across much of the Americas and remained one of the dominant hunters of its age for longer than our own genus has existed. By any reasonable measure, it should have outlasted almost everything around it. Yet the animal itself seemed to break the rules of what a predator should be. Its canine teeth were as long as a human forearm, yet they were too delicate to be used the way a lion uses its jaws. Its forelimbs carried more power than any living cat, built not for chasing prey across open ground, but for holding something still. Fossils show individuals surviving devastating injuries that should have left a solitary hunter unable to feed itself, raising a question that scientists are still trying to answer. And when it finally disappeared, it did not leave behind a single descendant. The entire branch of cats it belonged to vanished with it, ending an evolutionary story that had lasted more than 20 million years. For more than a century, researchers have tried to understand how a predator this successful could simply disappear. Even today, new evidence continues to reshape that picture. Whether you're settling in for the night or simply fascinated by the ancient world, I'm glad you're here. If you'd like to support the channel, a quick like and subscribe really does help. Now, let's step into the Ice Age and meet the predator whose greatest strengths may have become its greatest weakness. Names have a way of shaping the stories we tell, and few prehistoric animals have carried a more misleading name than the so-called saber-toothed tiger. The image feels familiar, yet it points in the wrong direction. Smilodon never belonged to the same branch of the cat family as modern tigers. The resemblance was only surface deep, while its ancestry followed an entirely different path through deep time. Long before the first tiger appeared, the ancestors of Smilodon had already begun a separate evolutionary journey that unfolded across roughly 20 million years, a span so immense that it exceeds the existence of our own genus. That forgotten branch became known as Machairodontinae, a subfamily unlike any living group of cats. Across millions of years, it developed its own body proportions, hunting methods, and solutions for bringing down large prey. Every member of that lineage has now disappeared. No descendant remains in forests, grasslands, mountains, or deserts. Lions, leopards, jaguars, cheetahs, pumas, and domestic cats all belong to different branches of the family tree. Smilodon shared distant ancestors with them, though its own lineage separated long before any modern cat had taken shape. Even Smilodon itself was never a single, unchanging animal. Paleontologists recognize three species, each appearing at a different point in time while preserving the distinctive features of the group. The earliest was Smilodon gracilis, emerging around 2,500,000 years ago. It carried a body closer in size to a modern jaguar, weighing between 55 and 100 kilograms, which is about 121 to 220 pounds. Its descendants gradually gave rise to larger forms as changing environments offered opportunities for increasingly powerful hunters. Around 1,600,000 years ago, Smilodon fatalis entered the landscape. This species reached the size of a large lion, weighing between 160 and 280 kilograms, which is about 353 to 617 pounds. Fossils of Smilodon fatalis have been recovered from many locations across North America, making it the species most people picture when imagining the famous saber-toothed predator. Farther south, another giant eventually appeared. Around 1 million years ago, Smilodon populators spread through South America and grew larger still. Some individuals exceeded 400 kilograms, which is about 882 pounds, placing them among the largest cats known from the fossil record. For nearly 500,000 years, all three species shared the planet, occupying different regions while representing successive chapters of the same remarkable lineage. Their combined range stretched from Alberta in Canada to the southern edge of South America, making Smilodon one of the most widespread large predators of the Ice Age. The name itself reaches back to the work of Danish paleontologist Peter Wilhelm Lund, who formally described the animal during the 19th century. He drew upon the Greek words smila, meaning knife, and odon, meaning tooth. Knife tooth became the lasting identity of a predator whose anatomy would eventually reveal one of evolution's most specialized designs, shaped through countless generations into something unlike any cat that still walks the earth. Few parts of any prehistoric animal have become as recognizable as the elongated canines of Smilodon. They appear powerful at first glance, inviting comparisons with the jaws of living lions or tigers. Careful study has revealed a far more intricate story. Those remarkable teeth represented an instrument of precision, shaped for a narrow purpose that demanded accuracy, restraint, and extraordinary control from the animal carrying them. In Smilodon fatalis, each upper canine extended about 18 centimeters below the lower jaw, which is about 7 feet. That is nearly 0.18 meters. The larger Smilodon populator carried canines exceeding 28 centimeters, which is about 11 inches. That is nearly 0.28 meters. Their length alone tells only part of the story. Viewed from the front, the teeth were surprisingly thin, flattened from side to side instead of rounded like the fangs of most living cats. Fine serrations trace their edges, giving them the appearance of carefully crafted blades instead of heavy spikes built for crushing impact. That elegant form carried an unavoidable compromise. The canines could slice deeply through soft tissue, though they tolerated very little sideways pressure. Modern lions often clamp onto struggling prey, while powerful twisting movements ripple through the neck and skull. Biomechanical research has demonstrated that the same motions would have placed dangerous stress across the skull of Smilodon. Computer models created by paleontologist Dr. Colin McHenry showed that applying roughly 200 kilograms of sideways force, which is about 441 pounds, produced strain throughout the skull far beyond what living lions experience under similar conditions. A comparable force leaves the skull of a lion comparatively stable because its teeth and jaws evolved for a different style of hunting. Another important detail appeared within the muscles responsible for closing the jaws. Those muscles were actually smaller than those of modern lions. Smilodon sacrificed raw bite strength in exchange for an unusually wide gape and greater reach. The mouth could open far enough to accommodate its elongated teeth, allowing them to enter the target at an angle impossible for living cats. Every feature reflected a specialized balance instead of a search for maximum force. Researchers later tested these ideas with a mechanical model designed to imitate the movement of a Smilodon skull. Informally called the RoboCat, the device pressed reconstructed jaws into the necks of bison and elk carcasses while reproducing realistic motion. The experiments consistently supported the same conclusion. The killing stroke depended upon a controlled downward movement of the head, while the jaws closed at the same moment. This combined action, often described as a canine shear bite, guided the blades into the soft tissues of the ventral neck, where large blood vessels lay close to the surface and no heavy bone blocked the path. Such a method left almost no room for improvisation. A misplaced strike against thick bone could shatter a canine that had taken years to grow. Every successful hunt therefore depended on reaching the final instant with the prey already restrained. The celebrated teeth did not begin the attack. They completed it, delivering a carefully placed wound only after every other part of the animal had created the conditions that allowed those extraordinary blades to be used safely. Every bone in the skeleton of Smilodon carried the imprint of a single requirement. The remarkable teeth described by the fossil record could perform their task only after the prey had stopped struggling. That condition shaped the rest of the animal from shoulders to paws, producing a predator whose body followed a design unlike any large cat alive today. Radiographic studies of Smilodon fatalis limb bones reveal exceptionally dense attachment points for powerful forelimb muscles. These features indicate strength beyond that seen in any living cat of comparable size. The forelegs were thick, heavily built, and capable of generating tremendous force over a short distance. Their purpose was neither graceful pursuit nor sustained running. They served as grappling tools, able to seize a large herbivore, drag it off balance, and pin it firmly against the ground, while every movement of the victim became smaller and more controlled. The shoulders formed the foundation of that system. Broad shoulder blades and massive muscle attachments created a stable platform capable of resisting the violent motions of struggling prey. Once contact had been made, the upper body could absorb tremendous stress without losing balance. This architecture differed sharply from that of the cheetah, whose lighter frame favors speed across open country. Smilodon followed the opposite path, exchanging endurance for concentrated power that could be released within only a few heartbeats. Its hind legs reflected the same pattern. They were comparatively short and heavily muscled, providing explosive acceleration over brief distances instead of prolonged pursuit. A chase lasting hundreds of meters, which is about 328 feet, would have favored faster predators with longer limbs and lighter bodies. Smilodon depended upon surprise. Cover allowed it to approach unnoticed before launching a rapid charge that ended almost as soon as it began. Success rested upon reaching the prey before it could gather full speed. Equally important was the neck. Thick cervical muscles connected the head to the shoulders with extraordinary strength, creating the force required for the downward motion identified by biomechanical studies. The neck did far more than support the skull. It became an active component of the final strike, driving the elongated canines into their intended target with controlled precision while reducing the chance of damaging those delicate blades. Seen together, the hunting sequence unfolded as a single coordinated system. An animal emerged from concealment, collided with its target, wrapped powerful forelimbs around the struggling body, forced it toward the ground, and held it steady. Only after complete control had been achieved could the carefully directed bite be delivered. Every movement depended upon the one before it, leaving little opportunity for improvisation if the sequence broke apart. Such a strategy flourished in landscapes where open feeding grounds blended with patches of woodland and dense vegetation. These mosaic habitats allowed large grazing animals to gather while providing concealed approaches for an ambush hunter. A modern leopard still demonstrates part of this logic when it relies upon strength and close range before carrying prey into a tree. Smilodon shared the same emphasis on physical control, although its anatomy committed almost every feature of its body to that purpose with far greater specialization. Within prey-rich landscapes, this design achieved extraordinary efficiency, though its remarkable precision left little room for adjustment when familiar conditions began to fade. Bones sometimes preserve more than anatomy. They preserve traces of relationships that vanished long before written memory. For many years, Smilodon was imagined as a solitary hunter moving through the Ice Age without companions. That picture began to change as paleontologists examined one remarkable collection of fossils, discovering evidence that hinted at lives shared rather than lived alone. The asphalt deposits at Rancho La Brea, in present day Los Angeles, have yielded the remains of more than 2,000 individual Smilodon, creating one of the largest fossil collections of any extinct predator ever assembled. Within those skeletons lay an unexpected pattern. More than 5,000 recovered bones display injuries that had healed long before death. Broken legs had knitted together, crushed chests showed signs of recovery, dislocated elbows had stabilized. Severe damage to the spine carried unmistakable evidence that the affected animals survived for months and sometimes years after wounds that would have made hunting extraordinarily difficult. One individual offered perhaps the strongest clue of all. Detailed computed tomography scanning revealed a cat born with severe hip dysplasia, a developmental condition that left the hip joint malformed from the earliest stages of life. The damaged limb would have prevented effective hunting, territorial defense, and independent survival from youth onward. Even so, the animal reached full adulthood. Such longevity suggests that food continued to arrive despite its inability to contribute in the same way as healthy adults. These discoveries opened an entirely different way of viewing Smilodon. If injured individuals regularly survived injuries that would have prevented successful hunting, some form of assistance becomes increasingly difficult to dismiss. Food may have been shared among members of a group. Healthy adults may have defended weakened companions until recovery became possible. Young animals with permanent disabilities may have remained protected within a social structure instead of being abandoned after birth. The fossils cannot record each interaction directly, though they preserve the consequences with remarkable clarity. Additional support emerged from research comparing the predator community at Rancho La Brea with modern ecosystems. Scientists from the University of California at Los Angeles and the Zoological Society of London examined the unusually high proportion of predators preserved alongside herbivores. Their analyses found that the numbers resembled communities dominated by social hunters more closely than those composed primarily of solitary carnivores. Cooperative living provided the most convincing explanation for such patterns, even though it could never be demonstrated by a single fossil alone. The discussion remains active within paleontology. Some researchers point to the relatively modest brain size of Smilodon, proposing that highly developed social behavior may have been unlikely. Others note that brain size alone cannot determine the complexity of behavior, especially when the fossil evidence consistently shows survival after devastating injuries. Each new specimen adds another fragment to the conversation without closing it completely. Among living cats, African lions provide the closest functional comparison. Pride members cooperate during hunts, defend shared territories, and feed injured companions that cannot immediately provide for themselves. Smilodon may have practiced a comparable strategy, allowing several adults to overwhelm prey far larger than any single hunter could safely control. Mammoths, giant ground sloths, and enormous bison would have become more manageable when strength and timing were shared across several animals instead of one. Seen through that possibility, the disappearance of Smilodon represents more than the loss of an extraordinary predator. It may also mark the end of a social world filled with enduring bonds, shared effort, and generations connected by care that can still be glimpsed through the enduring testimony of fossilized bone. An animal can often be understood by looking beyond its own body and toward the lives it depended upon. Smilodon belonged to an ecosystem where enormous herbivores shaped the rhythm of every season. The predator and its prey had evolved together across immense spans of time, each influencing the other until survival itself became a shared pattern written across the landscape. Columbian mammoths wandered through these environments with shoulders rising nearly 4 meters, which is about 13 feet, and some individuals weighed as much as 10 tons. Mastodons browsed among woodlands, feeding on branches and leaves instead of open grass. Giant ground sloths could rear to nearly 6 meters in height, which is about 20 feet, their curved claws extending almost the length of a human arm. Ancient bison outweighed many of their modern relatives. Native horses crossed broad plains in large herds. Glyptodonts carried armored shells over bodies approaching the size of a small automobile, while towering short-faced bears could stand roughly 12 feet tall, which is about 3.7 meters, on their hind legs. Every direction offered creatures whose scale feels almost unfamiliar today. Within that community, Smilodon occupied a highly specialized role. Evidence gathered from fossil chemistry indicates that large mammals formed almost the entirety of its diet. Stable isotope analysis examines chemical signatures preserved inside fossil bone collagen, allowing scientists to reconstruct what an animal consumed throughout much of its life. Those signatures consistently point toward large grazing and browsing herbivores as the principal source of nourishment. Small prey contributed little, if anything, to sustaining such a formidable hunter. The teeth support the same conclusion through another line of evidence. Dental microwear texture analysis examines microscopic scratches and pits left upon tooth enamel during feeding. Under powerful imaging techniques, the surfaces of Smilodon teeth resemble those of modern African lions, far more closely than bone-crushing carnivores such as hyenas. The patterns indicate repeated slicing through flesh while showing comparatively little evidence of habitual bone cracking. Smilodon fed efficiently from large carcasses without relying upon marrow hidden inside thick skeletal elements. This preference carried a profound consequence. Every feature already explored, from the specialized canines to the immensely powerful forelimbs, functioned most effectively against large herbivores. Small animals demanded different techniques. They twisted rapidly, changed direction without warning, and offered relatively little energy once captured. For a predator weighing around 200 kilograms, which is about 441 pounds, repeated hunts for animals only a fraction of that size would have consumed valuable strength while providing too little nourishment in return. Even scavenging offered limited flexibility. Many adaptable carnivores survive difficult periods by crushing large bones to reach calorie-rich marrow after other tissues have disappeared. Smilodon lacked that option. Attempting to force its elongated canines against heavy bone carried a genuine risk of fracture, transforming an already demanding hunt into a permanent injury that could threaten future survival. Every successful capture, therefore, represented a careful balance between effort and reward. Large prey justified the energy required for stalking, grappling, and delivering the final strike. Failure carried several costs at once. Precious energy had been spent. Another opportunity might not arrive soon. An uncontrolled struggle also increased the possibility of damaging the very tools upon which every future hunt depended. The Ice Age offered abundance for millions of years, and Smilodon became one of its greatest specialists by trusting that abundance would endure. Success in evolution is often measured by persistence, though another measure exists as well. Sometimes a lineage spreads into many forms at once, exploring different ways of surviving within the same world. The saber-toothed cats reached that moment of abundance long before their final representative walked across the plains of the Ice Age. Their greatest triumph arrived millions of years before their disappearance, leaving behind a chapter that is easily overlooked beside the fame of Smilodon itself. Research published during 2025 by scientists at the State University of Campinas traced the long history of the Mechaerodontinae subfamily through millions of years of fossil evidence. Their analysis showed that around 8 million years ago, the lineage reached its highest diversity. At least 8 distinct saber-toothed species occupied different continents at the same time, each adapted to its own ecological role. Today, only 7 species of large wild cats remain across the entire planet. During that earlier age, a single extinct branch of the cat family exceeded that diversity by itself. Those animals did not all resemble Smilodon. Some belong to a group commonly known as the scimitar-toothed cats. Among the best known was Homotherium, whose shorter, broader canines differed noticeably from the elongated blades carried by Smilodon. Its body was built with longer limbs and proportions better suited for covering greater distances. Instead of relying almost entirely upon close-range grappling, it appears to have combined speed with powerful slashing bites, opening a different path toward the same goal of bringing down large prey. Other members of the subfamily explored additional solutions. Certain species developed bodies better suited for pursuit across more open landscapes, while others retained heavier frames adapted to ambush. Together, they occupied a wide variety of habitats, reducing competition by specializing in different prey, different environments, and different hunting styles. The saber-toothed design was never a single invention frozen in time. It became an entire collection of evolutionary experiments, unfolding side by side across continents. For millions of years, this diversity remained surprisingly resilient. Fossil evidence suggests that roughly 5 saber-toothed species still coexisted around 6 million years ago. Their numbers had begun to contract, though the lineage continued producing formidable predators capable of dominating the ecosystems they inhabited. Among those later descendants, Smilodon represented perhaps the most refined expression of the dirk-toothed form. Its elongated canines, immense forequarters, and specialized hunting method carried the concept further than any known relative before it. Another remarkable opportunity appeared roughly 3 million years ago when the rising Panama Land Bridge connected North and South America during the Great American Interchange. Smilodon expanded southward into landscapes filled with unfamiliar megafauna and lacking established competitors among large cats. It spread successfully through this new continent, becoming one of its foremost predators, while extending its range farther than any earlier member of its lineage. By the time the Pleistocene arrived, Smilodon fatalis had already ruled much of North America for more than 1 million years. That span makes the whole of recorded human civilization appear astonishingly brief by comparison. Every indication suggested a lineage that had mastered its place with extraordinary confidence. Across millions of years, it had diversified, expanded, and flourished through changing continents. From the outside, its future appeared secure, even as a gradual change had already begun, within the deeper history of the lineage itself, too gradual to notice across a single lifetime, yet steadily reshaping its long inheritance. A long lived lineage can appear permanent when viewed through the span of a single lifetime. Fossils reveal a different perspective. They compress millions of years into layers of stone, allowing patterns to emerge that no living creature could ever witness. When paleontologists assembled the history of the saber-toothed cats across deep time, they found that the path toward extinction had begun far earlier than anyone once imagined. In 2025, Dr. João Nascimento and Dr. Matthias Pires of the State University of Campinas in Brazil published an extensive study in the Journal of Evolutionary Biology. Drawing upon approximately 15 million years of fossil evidence from North America and Eurasia, they reconstructed the rise and decline of the Mechirodontinae lineage with greater detail than had previously been possible. The picture that emerged did not resemble a sudden collapse brought about by one disastrous event. Instead, it showed a gradual pattern repeated again and again across geological time. Whenever the diversity of large prey animals declined, saber-toothed cats also disappeared. The relationship appeared with striking consistency throughout the fossil record. Changes in climate alone failed to explain every extinction. Competition from other predators could not account for the broader trend either. The strongest predictor remained the richness of available prey species. As ecosystems lost variety among large herbivores, specialized predators vanished in step with them. The timeline itself reflected this gradual erosion. Around 8 million years ago, the lineage reached its greatest diversity, with 8 known species living simultaneously. By roughly 6 million years ago, only about 5 remained. The contraction unfolded across millions of years, continuing through repeated environmental changes before ending with the disappearance of Smilodon around 10,000 years ago. What appears from a distance as one extinction was actually the final chapter of a much longer process. The fossil record also revealed regional differences. Across North America, the decline of saber-toothed cats closely tracked reductions within the horse family, scientifically known as equidae. Horses formed an important component of many Ice Age ecosystems, supporting numerous large predators. As horse diversity narrowed across regions, saber-toothed species frequently declined alongside them. This close relationship suggested that even abundant predators depended upon surprisingly delicate ecological foundations. Researchers describe part of this process as an evolutionary ratchet. With each generation, natural selection rewarded features that improved success under existing conditions. Longer slicing teeth, stronger forelimbs, and increasingly specialized hunting behavior all enhanced performance, while large prey remained plentiful. At the same time, every refinement reduced flexibility. The more efficient the predator became within one ecological setting, the fewer alternatives remained when that setting changed. Evolution continued, turning the ratchet forward, though it offered no easy path backward once specialization had deepened. This structural vulnerability existed millions of years before the first people entered the Americas. Human activity did not create the underlying dependence. It inherited a lineage already shaped by countless generations of increasing specialization. Even so, the fossil record shows that saber-toothed cats had survived earlier declines in prey diversity and continued evolving afterward. Recovery remained possible while ecosystems retained enough resilience to support it. By the closing stages of the Pleistocene, that resilience would face an unfamiliar combination of pressures arriving within the same broad span of time. The lineage had weathered changing climates before. It had endured earlier contractions in prey communities as well. The difference now rested in the convergence of forces that would reshape the world more completely than any previous challenge within the long history of the saber-toothed cats. For an immense stretch of time, the landscape rewarded the design that evolution had shaped with such extraordinary care. Herds crossed broad grasslands, patches of woodland offered concealment, and large herbivores remained plentiful enough to sustain predators built for powerful ambushes instead of prolonged pursuit. That balance endured through repeated cycles of cold and warmth. Around 14,700 years ago, however, familiar patterns across the northern hemisphere began changing with unusual speed. This interval, known as the Bowling-Olerud warming, followed the last glacial maximum and marked a rapid increase in global temperatures. Great continental ice sheets started withdrawing toward higher latitudes. Valleys opened where ice had stood for thousands of years. Rivers altered their courses as meltwater carved fresh channels across the land. Rising seas gradually reshaped coastlines, while vegetation zones shifted across entire continents. None of these transformations occurred in a single dramatic instant. They unfolded across generations, steadily rewriting the geography that countless species had depended upon. The changing climate reached far beyond temperature alone. Expansive grasslands that had nourished immense grazing animals gradually yielded to scrubland, woodland, and, across portions of North America, increasingly dry landscapes. Large herbivores depended upon productive open country capable of supporting enormous quantities of plant life. As those habitats contracted into smaller fragments, the animals themselves became more scattered. Food resources changed from broad connected systems into isolated patches, making seasonal movements more difficult and reducing the stability of once thriving populations. Evidence preserved within pollen grains and sediment layers from the Rancho La Brea region tells an equally revealing story. Southern California experienced prolonged periods of severe drought lasting many generations before the final disappearance of Smilodon. These extended dry intervals reduced plant productivity while reshaping local ecosystems from the ground upward. Each season placed greater strain upon grazing animals already adapting to changing vegetation. The pressure accumulated gradually, leaving subtle marks in the geological record long before the last saber-toothed cat vanished. As broad habitats fragmented, populations of large mammals became increasingly separated from one another. Continuous grasslands that had once stretched across great distances broke into disconnected landscapes. Smaller groups of herbivores carried greater risk of local disappearance through disease, harsh weather, or simple chance. Predators depending upon those animals inherited the same growing instability. A hunting territory that had supported abundant prey for thousands of years could become far less dependable without any sudden catastrophe announcing the change. Radiocarbon dating from Rancho La Brea reflects the opening stages of that biological cascade. Around 13,600 years ago, giant ground sloths and North American camels disappeared from the local fossil record. Their absence represented more than the loss of individual species. Each disappearance narrowed the range of prey available to large, specialized hunters, making every remaining food source increasingly valuable. Smilodon occupied a particularly delicate position within this changing world. Its hunting strategy depended upon mosaic habitats where cover stood close to open feeding grounds. Those environments ranked among the first to transform as vegetation shifted. At the same time, the large herbivores supporting its specialized diet became fewer and more dispersed. Predator and prey were changing together, each responding to the same reshaped landscape. Even this did not guarantee extinction. Smilodon and its ancestors had already survived at least 12 earlier ice ages, enduring repeated climatic fluctuations across millions of years. Climate alone had never erased the lineage. The difference during this final transformation rested elsewhere, emerging alongside environmental change as another force entered the Americas during the same remarkable span of time. Across the changing landscapes of the Late Ice Age, another presence entered the story with measured footsteps. While grasslands contracted and familiar hunting grounds became less dependable, people were also moving into the Americas. The environmental transformation had already placed strain upon the great animals of the continent. Human arrival introduced a second influence that operated in an entirely different way, one grounded in behavior, cooperation, and technology, rather than climate alone. Current evidence indicates that people reached North America sometime between roughly 20,000 and 15,000 years ago. Some groups likely crossed from northeastern Asia over the Bering Land Bridge, exposed when lower sea levels connected the continents. Others may have followed the Pacific coastline by water and along the shore. These possibilities are no longer viewed as competing stories, but as routes that may both have contributed to the settlement of a previously unoccupied continent. The large mammals of North America already understood wolves, bears, and other familiar predators. Those relationships had been shaped through countless generations of natural selection. Human hunters represented something entirely different. They coordinated their movements, planned ahead, communicated complex information, and carried carefully crafted weapons capable of striking from a distance. Selection can gradually teach prey species how to recognize recurring dangers, yet those lessons require many thousands of generations. A newly arrived predator offers no such opportunity. Behavioral caution cannot appear fully formed within only a few centuries. This distinction becomes clearer when compared with Africa. There, elephants, antelope, buffalo, rhinoceroses, and other large mammals shared landscapes with members of the human lineage for hundreds of thousands of years. Species including Homo erectus, Homo heidelbergensis, and eventually Homo sapiens became enduring features of those ecosystems. Animals that consistently reacted too slowly or too carelessly were less likely to survive and reproduce. Across immense spans of time, heightened awareness of upright tool using hunters became woven into normal behavior. The American megafauna inherited no equivalent history. The same pattern appears repeatedly beyond the Americas. Australia experienced widespread megafaunal losses after human arrival roughly 46,000 years ago. Madagascar followed a comparable sequence much later, as did New Zealand and numerous island ecosystems scattered across the oceans. Each region possessed its own climate, geography, and collection of animals, yet the arrival of people repeatedly coincided with substantial ecological change. Those similarities have become an important part of the broader scientific discussion surrounding late prehistoric extinctions. One striking comparison comes from Wrangel Island in the Arctic Ocean. Woolly mammoths disappeared from continental landscapes thousands of years earlier. Yet, an isolated island population survived until about 4,000 years ago. The island remained beyond the reach of human settlement during most of that interval. Isolation did not make the mammoths immortal, but it demonstrates that some megafaunal populations could persist long after their mainland relatives had vanished when human contact remained absent. Archaeological discoveries place people within the extinction window itself. Distinctive Clovis spear points, carefully shaped from stone with broad symmetrical blades, were well suited for hunting large mammals. Their appearance across North America reflects organized hunting traditions directed toward enormous prey. In the Los Angeles basin, the fossil known as the La Brea woman offers rare evidence that Paleo-Indian hunter-gatherers occupied the same region while the great mammals were disappearing. Climate had already weakened the ecological foundation. Human beings entered a landscape where that long unfolding change was reaching its most delicate balance. A solution to the long argument emerged from an unexpected source. The evidence did not point toward a choice between climate and people. It pointed toward an interaction. The landscape itself became the place where both influences met, each amplifying the other, until the balance that had endured for so long could no longer recover. In 2023, a team of 19 researchers published a study in the journal Science that examined the extinction history preserved at Rancho La Brea with unprecedented detail. Their investigation drew upon 172 newly established radiocarbon dates taken from fossils belonging to 8 major species. Those dates were compared with pollen records, charcoal deposits, and evidence tracking the spread of human populations across North America. The resulting model became the most statistically rigorous reconstruction yet produced for the Southern California extinction sequence. The charcoal record revealed a striking pattern. Regional wildfire activity increased dramatically during the same interval that the great mammals disappeared. This surge in burning appeared before the final extinction pulse and expanded across the landscape as climatic conditions became warmer and progressively drier. Fire had always been a natural component of many ecosystems. The difference lay in its frequency, extent, and persistence. The landscape was no longer recovering between burn events. Each fire altered the environment in ways that encouraged the next. Researchers describe this process as an ecological state shift. The phrase refers to a threshold beyond which an ecosystem settles into an entirely different condition instead of returning to its previous form. Productive grasslands and mixed woodland, capable of supporting immense grazing animals, gradually gave way to brush-dominated terrain and expanding desert. Once that threshold had been crossed, the older ecosystem did not readily reappear, even when environmental conditions later fluctuated. The transformation became self-reinforcing. The sequence itself also became clearer. Climatic warming increased aridity across Southern California, drying vegetation and making extensive fires increasingly likely. Human communities, whether through intentional landscape burning or the accidental spread of fire, introduced additional ignitions into an environment already primed to burn. Neither influence alone adequately explained the fossil evidence. Together, they produced a cascading ecological transition that unfolded across only a few centuries, remarkably swift when measured against the millions of years that had shaped Smilodon. The revised chronology also challenged a long-favored explanation. For many years, the Younger Dryas cooling interval, beginning around 12,900 years ago, had been regarded as the principal driver of extinction in the region. The new radiocarbon framework demonstrated that most of the large mammals represented at Rancho La Brea had already vanished before that climatic reversal began. Giant ground sloths and camels disappeared by roughly 13,600 years ago. Horses followed. Soon afterward, Smilodon, dire wolves, and American lions also vanished from the record. The timing no longer supported the Younger Dryas as the primary cause. The debate therefore changed from an either-or question into a broader ecological story. Warming produced an increasingly combustible landscape. Human activity supplied additional opportunities for widespread burning. Together, they pushed an already strained ecosystem beyond its capacity to recover. The authors concluded with words that reached beyond the Ice Age itself, describing their findings as reflecting an ominous parallel to challenges that humans are confronting on a planetary scale today. Those words were offered within a peer reviewed scientific paper, grounded in evidence drawn from one of the world's richest fossil archives. Loss did not arrive all at once. It unfolded species by species, each disappearance narrowing the possibilities available to a predator whose entire existence depended upon an abundance of very large herbivores. Every successful hunt now carried greater significance because another familiar target had already faded from the landscape. Evolution had refined Smilodon for extraordinary efficiency within a stable world. That same refinement became increasingly difficult to sustain as the foundation beneath it steadily dissolved. The sequence can be traced through the fossil record. Giant ground sloths and North American camels disappeared from some regions first. Horses followed as their populations declined across broad areas. Ancient bison became less numerous and more unevenly distributed. Mastodons also diminished, while mammoths gradually vanished from many parts of the continent. Each reduction removed another dependable source of food. No single extinction guaranteed the downfall of Smilodon, yet every loss reduced the resilience of a hunting system that had little room for compromise. The demands placed upon such a predator were immense. An adult Smilodon, weighing around 200 kilograms, required a substantial and dependable supply of meat to maintain its powerful muscles, recover from injuries, and support daily activity. Large prey delivered enormous nutritional rewards from a single successful hunt. When those animals became scarce, the distance traveled between opportunities increased, while every failed ambush consumed valuable energy that could not easily be replaced. Turning toward smaller animals offered little relief. The famous canine teeth had evolved for a carefully controlled strike against large prey held securely beneath powerful forelimbs. Smaller mammals behaved very differently. They twisted, darted, kicked, and changed direction with remarkable speed. Those rapid, unpredictable movements increased sideways stress upon the elongated canines, exactly the type of force biomechanical studies suggest they were poorly suited to withstand. The hunting sequence itself had evolved around controlling heavy bodies, not pursuing numerous fast-moving targets. Even success carried diminishing returns. Catching a comparatively small animal required effort that often yielded only a fraction of the calories provided by a mammoth calf, a horse, or a large bison. The balance between energy spent and energy gained shifted steadily in the wrong direction. An animal built upon abundant large prey could not indefinitely sustain itself through meals that barely replaced the energy invested in obtaining them. Generalist predators possessed another advantage that Smilodon lacked. Species capable of crushing heavy bones could reach nutrient-rich marrow after the surrounding flesh had been consumed. That flexibility became especially valuable during periods when fresh kills were uncommon. Smilodon's elongated and comparatively delicate canines made such feeding behavior risky and inefficient. The design that excelled during prosperous times offered fewer alternatives as resources dwindled. The shrinking distribution of prey also separated predator populations from one another. As suitable hunting grounds became isolated pockets instead of connected landscapes, groups of Smilodon likely became increasingly fragmented. Smaller populations exchanged fewer individuals, reducing genetic diversity and limiting their ability to recover from disease, accidents, or further environmental disruption. Evidence from Rancho La Brea adds one final detail. Fossils from later populations show elevated frequencies of broken canine teeth. Some researchers suggest this pattern may reflect increasing desperation, with hunters attempting prey or attack angles outside the safer limits established by millions of years of specialization. Every broken tooth reduced the chance of future success. Every failed hunt demanded another attempt. As prey declined further, injuries accumulated, populations contracted, and the remarkable hunting system that had once flourished found itself enclosed within an ecological trap from which its own evolutionary history offered no escape. The final chapter of Smilodon's decline contains an unexpected simplicity. No battlefield of fallen saber-toothed cats marks the closing scene. No archaeological record reveals widespread hunting of the predator itself. The decisive change unfolded one step lower in the food web, where the great herbivores, sustaining the entire Ice Age community, were already struggling to persist. By removing those animals, humans altered the fate of a hunter they may never have deliberately pursued. The process followed a principle that ecologists describe as a trophic cascade. In its simplest form, the pattern begins when the abundance of prey falls beyond a sustainable threshold. Predators depending upon those animals soon experience the same decline because every successful hunt becomes less frequent. Every territory supports fewer individuals, and each generation raises fewer young. The collapse travels upward through the food chain almost automatically. Smilodon occupied the highest level of that chain, making it especially vulnerable once the foundation beneath it weakened. Human hunters entered this changing landscape, while mammoths, mastodons, giant ground sloths, horses, and other large herbivores were already under pressure from shrinking habitats and repeated ecological disruption. Every successful hunt removed another breeding animal from populations that had become smaller and more fragmented than before. Climate had reduced the available resources supporting these giants. Human hunting accelerated the reduction by drawing from the very same populations. Both pressures acted upon a single shared source of life. Evidence gathered so far offers little indication that people regularly hunted Smilodon itself. Archaeologists have not discovered confirmed kill sites containing saber-toothed cats alongside unmistakable evidence of human butchery. Smilodon bones bearing clear stone tool marks remain absent from the known record. Neither do these predators appear as a recognizable component of documented human diets from the closing stages of the Ice Age. Their disappearance can therefore be understood without placing humans and saber-toothed cats into repeated direct conflict. Competition still existed, although it unfolded indirectly. Human hunters sought many of the same large herbivores that sustained Smilodon. Every mammoth, horse, mastodon, or giant ground sloth harvested by people represented food no longer available to nearby predators. Across a broad continent and through many generations, those individual losses accumulated into a measurable ecological burden. The contest centered upon resources instead of confrontation. This perspective also reshapes the familiar overkill hypothesis. The crucial effect did not require the systematic killing of apex predators. Eliminating enough of their prey achieved the same outcome for species whose bodies had become tightly linked to particular food sources. Smilodon had evolved into one of the most specialized hunters the mammalian world ever produced. That remarkable specialization left little capacity to absorb prolonged reductions in the abundance of large herbivores. Comparable processes continue to appear in modern ecosystems. Across parts of Africa and Asia, Heavy hunting of hoofed mammals has reduced food supplies for lions, leopards, and other large carnivores. Predator numbers often decline, even where direct persecution remains limited, because the animals they depend upon have already become scarce. The ecological relationship remains unchanged despite the passing of thousands of years. A hunter that possessed no natural predator eventually disappeared through the loss of everything supporting its existence. Its extraordinary strength, precision, and refinement remained intact until the end. The world surrounding those qualities changed first, and once that world faded, even one of evolution's greatest predators could no longer endure. Few scientific discussions have endured as long as the question surrounding the disappearance of the Ice Age giants. More than a century and a half of discoveries has filled museums with fossils, expanded radiocarbon dating, refined climate records, and transformed the study of ancient ecosystems. Even so, the central argument remains active. The persistence of that disagreement reflects the complexity of extinction itself, where several forces may gather until none can be separated from the others. One explanation places climate at the center of the story. Supporters point to the rapid warming that followed the final glacial maximum, the transformation of grasslands into woodland and brush, and the steady reduction of habitats capable of sustaining enormous grazing mammals. Under this view, the collapse of prey communities eventually carried specialized predators with them. Critics respond that Smilodon and its relatives had already endured at least 12 previous glacial cycles across millions of years. Earlier climatic swings had altered landscapes without permanently ending the lineage, suggesting that temperature alone cannot fully explain the final outcome. A different interpretation gained prominence through the work of Dr. Paul Martin, whose Blitzkrieg model proposed that expanding human populations rapidly overwhelmed prey animals, lacking evolutionary experience, with organized hunters. Across much of the world, the disappearance of large mammals follows human arrival with striking consistency. Australia lost most of its giant animals after people appeared. Comparable patterns later unfolded across Madagascar, New Zealand, and many island ecosystems. Those repeated associations encouraged the view that human expansion itself supplied the decisive pressure. Africa presents the strongest challenge to a climate only explanation. The continent experienced the same broad climatic changes affecting the rest of the world, yet much of its large mammal community survived into the present. Elephants, rhinoceroses, giraffes, lions, and many other giants continued sharing the landscape with people. Their ancestors had evolved alongside successive human relatives over hundreds of thousands of years, gradually developing behaviors suited to that relationship. The contrast implies that another variable operated beyond climate alone. Islands provide another revealing comparison. Woolly mammoths persisted on Wrangel Island until about 4,000 years ago, thousands of years after disappearing from the mainland. Giant ground sloths survived on Caribbean islands long beyond their continental relatives. Steller's sea cows remained on the remote Commander Islands until human arrival reached them during historical times. Again and again, isolated populations without sustained human contact endured beyond mainland extinction. For Smilodon itself, uncertainty remains genuine. No confirmed evidence demonstrates systematic hunting of saber-toothed cats by people. Archaeologists have not uncovered convincing kill sites or unmistakable tool marks on their bones. The strongest evidence instead supports an indirect pathway, where shrinking prey populations steadily undermined the predator's survival. That relationship is reconstructed from fossils, ecological modeling, and chronological evidence rather than direct observation. Many researchers now favor a synthesis joining these perspectives. The comprehensive study, published during the year 2023 from Rancho La Brea, identified widespread wildfire as the mechanism connecting climatic drying with expanding human influence. Warming created landscapes increasingly vulnerable to burning. Human activity supplied widespread ignition. Together, they pushed ecosystems across a lasting ecological threshold that transformed productive habitat into environments supporting far fewer giant herbivores. The debate, therefore, endures because extinction rarely follows a single path. Separate pressures may appear modest when viewed alone, yet together they become inseparable strands of one unfolding history. Even with one of the richest fossil records ever uncovered, understanding that history demands patience equal to the immense span of time that created it. There came a day, sometime around 10,000 years ago, when a single Smilodon drew its final breath without another of its kind remaining anywhere beyond the horizon. No witness recognized the moment. No trace in the landscape marked its passing. Life continued across the continents as rivers flowed. Grasses returned with the seasons, and other creatures filled the spaces left behind. One lineage that had endured for roughly 2.5 million years had reached its final living chapter. Conservation biology now uses a word for such an individual, the endling. The term first appeared through informal discussion before gradually entering scientific language as modern extinctions became increasingly documented. An endling is the last known living member of a species, carrying an entire evolutionary history within a single body. When that individual dies, every inherited behavior, every unique genetic combination, and every future generation disappear together. The event is both biological and historical, closing a story that can never be reopened. The fossil record from Rancho La Brea suggests that Southern California lost its Smilodon population before approximately 12,900 years ago. Radiocarbon dating places the youngest confirmed remains before that point, indicating that this famous population vanished relatively early within the broader continental decline. Other regions persisted for a time, though the pattern remained the same. Local disappearances accumulated until the species itself no longer occupied any part of its former range. By approximately 10,000 years ago, Smilodon had disappeared from both North America and South America. A predator that had crossed continents, adapted to changing environments, and dominated Ice Age ecosystems across an immense geographic range had contracted into nothing. The disappearance unfolded within a comparatively narrow span of time when measured against the millions of years that preceded it. The closing act proved remarkably brief beside the extraordinary length of the story itself. Those final populations were unlikely to resemble the thriving communities that had once spread across productive landscapes. Small groups probably occupied isolated pockets where suitable habitat and remaining prey still overlapped. Distance separated them from neighboring populations. Genetic diversity narrowed as opportunities for exchange diminished. Every unsuccessful breeding season, every failed hunt, and every local loss carried greater weight because fewer individuals remained to sustain the lineage. Rancho La Brea may also preserve a glimpse of those closing generations through the carnivore trap itself. Distressed herbivores became caught near water sources and sticky asphalt seeps, attracting hungry predators seeking increasingly valuable meals. As natural hunting opportunities declined, these sites may have grown more significant as places where scarce food could still be found. The same conditions that drew the last Smilodon toward an uncertain meal eventually protected their bones beneath layers of sediment, allowing their story to survive after the animals themselves had vanished. Unlike the disappearance of the non avian dinosaurs, no asteroid ended the reign of Smilodon. No global volcanic winter erased it within days. Its extinction accumulated through decades and centuries as environmental change, shrinking prey populations, expanding human influence, and ecological instability reinforced one another. Each pressure alone might have remained survivable. Together, they steadily removed every path toward recovery. Today, endlings are no longer ideas drawn only from fossils. The final Rab's fringe-limbed tree frog and the last male northern white rhinoceros have each carried that title within living memory. Their names remind us that extinction is often not a dramatic ending. More often, it concludes with one remaining life, followed by an absence so complete that only memory, bones, and careful science continue the story. The disappearance of Smilodon marked far more than the loss of a single predator. By the close of the Pleistocene, North America had undergone one of the greatest biological reductions in its recent geological history. Around 70% of large mammals weighing more than 40 kilograms, which is about 88 pounds, had vanished. Close to 100 species disappeared within a comparatively brief span of time, leaving ecosystems that looked familiar in outline but profoundly different in substance. Among those losses were the dire wolves, heavily built social hunters whose fossil record is preserved in extraordinary numbers at Rancho La Brea. More than 4,000 individuals have been recovered there, offering an unusually detailed glimpse into a predator that no longer roams the continent. The American lion also vanished. Larger than any living African lion, it represented the greatest lion ever known from the fossil record. Nearby lived the short-faced bear, an immense carnivore capable of standing nearly 12 feet tall on its hind legs, which is about 3.7 meters, and believed to have been among the fastest bears across short distances. Other disappearances reveal equally remarkable stories. North America once supported its own lineage of cheetahs, separate from the living species of Africa and Asia. Their presence may explain why the pronghorn antelope evolved such extraordinary speed, preserving an escape strategy shaped by a predator that eventually vanished. Horses present an even more surprising history. They first evolved in North America before spreading into Asia and Europe across ancient land bridges. After thriving for millions of years, they disappeared from the continent of their origin. The horses that later became symbols of the American West arrived only after Spanish expeditions introduced them during the 1500s. The list continued across nearly every corner of the landscape. Columbian mammoths disappeared alongside mastodons. Giant ground sloths no longer browsed woodlands and open country. Glyptodonts, protected by immense armored shells, vanished from the southern reaches of the continent. Native camels, whose ancestors had also originated in North America before spreading elsewhere, faded from the fossil record. Each extinction removed another thread from an ecological fabric that had been woven over millions of years. The consequences extended beyond individual species. Large herbivores shaped vegetation through grazing and browsing. Massive predators regulated herbivore numbers and behavior. Scavengers depended upon the remains left behind. Once these relationships unraveled, the structure of entire ecosystems shifted. A continent that had supported an astonishing variety of giant animals settled into a simpler arrangement with far fewer large bodies moving across its plains, forests, and valleys. Only a handful of predators endured. The coyote survived through remarkable dietary flexibility, feeding on prey that ranged from insects to deer. The puma persisted, because it could hunt animals of many different sizes across varied habitats. Smaller carnivores also adapted by changing food sources as conditions changed. Generalists proved more resilient than specialists, whose survival depended upon a narrow ecological role. The world that remained still carried mountains, rivers, and grasslands, yet one of its defining communities had dissolved. Smilodon disappeared together, with companions that had shared its age, its prey, and its landscapes. Their absence reminds us that extinction often reaches across an entire network of life, leaving behind an Earth that continues forward, though fundamentally transformed. Long after the final Smilodon vanished, its story remained locked inside materials that appeared almost ordinary. Bones rested within dark asphalt deposits. Teeth preserved faint marks left by countless meals. Even tiny traces of ancient proteins and chemical elements endured across thousands of years. Piece by piece, researchers learned that extinction could be reconstructed without witnesses, provided they understood how to interpret the evidence that time had spared. One of the most important tools is radiocarbon dating. Living organisms continually absorb a naturally occurring form of carbon. After death, that form of carbon begins to decay at a steady and measurable rate. By calculating how much remains, scientists can estimate when an animal lived. Rancho La Brea offers an unusual advantage because the surrounding asphalt helped preserve collagen within many bones. At most fossil sites, collagen disappears long before researchers can examine it. Here, many individual fossils still contain enough surviving material to be dated with remarkable precision, allowing entire populations to be arranged into a reliable timeline. Achieving that precision required years of methodological refinement. Asphalt protects fossils, yet it also introduces petroleum compounds that interfere with radiocarbon measurements. Researchers developed specialized laboratory techniques to separate original biological material from surrounding contaminants before dating could begin. That achievement became a foundation for the detailed chronology published during the recent La Brea extinction research. Without those procedures, many of the timelines now used to understand the closing chapters of the Ice Age would have remained uncertain. Teeth preserve another record. Through dental microwear texture analysis, scientists examine enamel using confocal microscopy to produce detailed three-dimensional maps of microscopic wear. Fine, parallel scratches usually reflect repeated slicing through soft flesh. Deeper pits point toward greater contact with hard materials such as bone. Each feeding habit leaves a distinctive signature. Even after thousands of years, those surfaces preserve a history of meals that can still be read with extraordinary clarity. Chemical evidence extends the story further. Stable isotope analysis measures naturally occurring forms of elements preserved inside bone collagen. Those chemical patterns reflect the foods an animal consumed throughout its lifetime. From them, researchers can infer preferred prey, recognize differences between neighboring populations, and sometimes detect seasonal movements across changing landscapes. Instead of preserving a single moment, the skeleton carries a biological record accumulated over many years. Modern imaging contributes another layer of understanding. Computed tomography scanning reveals internal bone structure without cutting or damaging valuable fossils. Hidden fractures, healed injuries, and developmental conditions become visible inside the skeleton itself. One celebrated Smilodon specimen displaying severe hip dysplasia demonstrated that the animal survived for years despite a debilitating condition Evidence consistent with prolonged care or food sharing within at least some groups. Other questions remain more difficult. Ancient deoxyribonucleic acid has transformed the study of animals preserved in frozen ground, yet asphalt creates a very different chemical environment that damages genetic material. Researchers continue refining extraction methods, hoping future advances may recover usable sequences from Rancho La Brea specimens. Each improvement promises another layer of biological detail. Together, these approaches have transformed scattered fossils into a remarkably complete portrait of Smilodon, revealing its anatomy, diet, injuries, and ecological relationships with far greater confidence than was possible only a few decades ago. Even so, important mysteries remain. The precise timing of the final South American populations, the possibility of isolated survivors beyond the currently accepted dates, and many aspects of social behavior still await evidence resting somewhere within the geological record. One continent followed a different path. While enormous mammals disappeared across much of the Americas, Australia, and large parts of Eurasia, Africa retained an extraordinary assembly of giant animals that still survives today. Elephants continue shaping forests and grasslands. Rhinoceroses, hippopotamuses, giraffes, lions, leopards, cheetahs, spotted hyenas, and African wild dogs remain part of living ecosystems. Their continued presence offers one of the strongest clues for understanding why Smilodon and so many of its contemporaries vanished elsewhere. A widely supported explanation centers on a partnership forged over immense spans of time. African megafauna evolved alongside successive human relatives, including Homo erectus, Homo heidelbergensis, and eventually Homo sapiens. For hundreds of thousands of years, these animals encountered upright hunters that carried tools, cooperated in groups, and gradually became more effective at capturing large prey. Each generation faced similar pressures, allowing natural selection to favor individuals that recognized danger sooner and responded more effectively. Behavior can evolve just as anatomy does. Animals that hesitated when humans approached were less likely to survive and reproduce. Individuals that detected people from greater distances, fled earlier, or avoided familiar hunting grounds gained an advantage that could be passed through future generations. Across many thousands of years, this repeated selection gradually produced populations with deeply ingrained caution toward human hunters. Such responses did not appear within a single lifetime. They accumulated across countless generations. The large mammals of North America inherited a different history. Before people entered the continent, no predator combined upright movement, coordinated planning, projectile weapons, and sophisticated communication. Wolves hunted in packs, large cats relied on stealth, and bears depended on strength, yet none resembled human hunters. When people eventually arrived, many prey species lacked an inherited behavioral framework for responding to this unfamiliar threat. Their instincts had been shaped by predators they already knew, leaving little evolutionary preparation for a new kind of opponent. Australia presents another striking comparison. Around 46,000 years ago, giant kangaroos, rhinoceros-sized diprotodons, and the formidable marsupial lion disappeared within a period that broadly coincided with human arrival. Although climate also changed during that interval, the timing has encouraged many researchers to conclude that people became an important contributing factor there as well. Similar patterns appear repeatedly in regions where large animals encountered humans without a prolonged history of coexistence. Island ecosystems strengthen the same observation. Woolly mammoths survived on Wrangel Island for thousands of years after mainland populations disappeared. Giant ground sloths endured on Caribbean islands beyond their continental relatives. Madagascar preserved its remarkable giant animals until human settlement, after which many disappeared within a comparatively short period. Although each location possessed its own environmental history, the repeated association between human arrival and later megafaunal decline remains difficult to ignore. Africa, therefore, serves less as an exception than as a natural comparison. It suggests that long coexistence may have provided wildlife with time to adapt behaviorally to an increasingly capable predator. Whether North American megafauna, including Smilodon, might have followed a similar path if human expansion had unfolded across many tens of thousands of years, instead of a comparatively rapid interval, cannot be answered from the available evidence. Even so, the comparison reveals how deeply evolutionary history can influence survival when familiar worlds begin to change. Perfection can become a prison when the world that shaped it begins to disappear. For more than 2 million years, Smilodon followed an evolutionary path that rewarded increasing precision. Every generation refined the same remarkable design: longer saber teeth, stronger forelimbs, reinforced neck muscles, and carefully limited jaw mechanics, all combined into a predator capable of dispatching enormous prey with extraordinary efficiency. Across stable Ice Age ecosystems, each refinement brought another advantage. Evolution had little reason to preserve abilities that no longer contributed to survival. Specialization is one of nature's most successful strategies when conditions remain dependable. A specialist does one task better than almost any competitor, spending less energy while achieving greater success. A generalist accepts compromise, performing many tasks adequately without mastering any of them, as long as familiar prey remained abundant across broad landscapes. Smilodon occupied the favorable side of that balance. Every successful hunt reinforced the value of becoming even more specialized, allowing natural selection to continue narrowing its focus across countless generations. The difficulty emerged when the environment shifted faster than evolution could respond. Natural selection works through reproduction, inheritance, and gradual change spread across thousands of generations. The closing centuries of the late Pleistocene unfolded on an entirely different timetable. Habitats transformed, prey communities contracted, and ecological relationships unraveled within a span far too brief for a large mammal to develop fundamentally different adaptations. The interval between environmental change and evolutionary response became impossibly wide. Each feature that once defined Smilodon's success also narrowed the situations in which that success remained possible. Its elongated canine teeth excelled at delivering carefully placed killing bites into large herbivores held securely beneath powerful forelimbs. Those same teeth offered little flexibility for pursuing much smaller prey. Massive shoulders and grappling limbs represented an investment in strength instead of endurance. Even its comparatively modest bite force reflected another evolutionary trade. Modern lions generate greater crushing power, while Smilodon sacrificed some of that force in exchange for wider jaw opening and the precise killing technique demanded by its extraordinary canines. Every improvement increased effectiveness within one ecological setting while reducing options outside it. Modern animals reveal comparable patterns. Cheetahs remain unmatched in explosive acceleration, yet that specialization carries substantial costs, including metabolic demands, vulnerability after exhausting chases, and reduced genetic diversity. Giant pandas survive almost entirely on bamboo, tying their future to the persistence of a single food source across an increasingly fragmented landscape. Neither species is poorly adapted. Each stands among evolution's finest specialists within the conditions that shaped them. The survivors of the late Pleistocene generally shared another quality. Coyotes shifted between rodents, rabbits, insects, fruit, carrion, and countless other opportunities depending on what each season offered. Ravens accepted nearly any available source of nourishment. Such flexibility prevented dependence upon one disappearing resource. Their success rested less upon mastering a single strategy than upon abandoning one whenever circumstances demanded another. Smilodon possessed no comparable reserve. Its remarkable anatomy represented millions of years of refinement concentrated into one highly effective solution. Within the Ice Age ecosystems that produced it, few predators could rival its abilities. Once those ecosystems dissolved, the same precision became a constraint. Evolution had built an animal almost perfectly suited to a familiar world. When that world faded, perfection itself became the final disadvantage. Extinction often leaves echoes behind. A species may vanish while close relatives continue carrying fragments of its evolutionary story into the future. Those surviving branches preserve inherited anatomy, behavior, and genetic history, allowing an ancient lineage to continue in altered forms. Smilodon reached a different ending. When the final members disappeared, no descendant remained to inherit what millions of years had created. An entire branch of the tree of life ended where it stood. Smilodon belonged to the subfamily Machirodontinae, the saber-toothed cats. This remarkable lineage endured for roughly 23 million years, an interval so immense that it exceeds the span separating the present day from the earliest true primates. Across those millions of years, the group diversified into many forms that spread through Africa, Eurasia, North America, and South America. Different species rose and disappeared as climates shifted and ecosystems changed, yet the lineage itself continued. By the closing chapters of the Ice Age, Smilodon represented the final genus of the final surviving tribe within that ancient subfamily. When it disappeared, Machirodontinae disappeared with it. That outcome differs profoundly from the extinction of a single species. If one modern leopard population vanished today, other leopard populations would preserve its broader evolutionary heritage. Even if leopards themselves disappeared, lions, jaguars, tigers, and snow leopards would continue representing their shared lineage. Entire branches would remain alive. The extinction of Machirodontinae severed the whole branch permanently. No living animal carries that evolutionary inheritance forward. This also explains a widespread misunderstanding. Modern big cats are not descendants of Smilodon. Lions, tigers, jaguars, leopards, and snow leopards belong to the subfamily Pantherinae. Pumas, cheetahs, lynxes, bobcats, and domestic cats belong to the subfamily Felinae. Their shared ancestry with the saber-toothed cats reaches back approximately 20 million years before the present. Since that distant separation, each lineage followed its own evolutionary course, producing very different solutions to life as large predators. Even more remarkable, the saber-toothed design appeared repeatedly in entirely separate branches of mammalian history. Thylacosmolus evolved elongated saber teeth in South America despite belonging to the marsupials instead of the true cats. Nimrovids developed similar hunting adaptations while remaining outside the true cat family altogether. Certain creodonts also evolved enlarged saber-like teeth through independent evolutionary pathways. Large prey repeatedly presented the same challenge, and evolution repeatedly arrived at a strikingly similar answer. Every one of those lineages has now disappeared. That pattern reveals both the power and the limits of evolution. Natural selection can discover highly effective solutions more than once when similar ecological conditions exist. Those solutions may flourish across millions of years, dominating entire continents through countless generations. Their repeated appearance demonstrates extraordinary effectiveness. Their repeated disappearance reveals that effectiveness always depends upon the world that shaped it. The saber-toothed experiment lasted across geological ages, surviving changing continents, shifting climates, and innumerable ecological transformations. It produced some of the most specialized predators ever to walk the earth. Then, within a comparatively brief interval, every branch carrying that remarkable design came to its end. No descendant remained to soften the loss. The lineage left fossils, lessons, and an empty place on the tree of life where an entire chapter once grew. The distance between the Ice Age and the present can seem immeasurable, yet the patterns that shaped one world still appear in another. The great cats living today move through landscapes transformed by different forces, but many of the pressures surrounding them follow familiar pathways. Their story is not a repetition of Smilodon's fate, though the underlying processes often resemble those preserved in the fossil record. The lion offers one of the clearest examples. During the middle of the 20th century, scientists estimate that roughly 200,000 lions lived across Africa and parts of Asia. Today, only about 20,000 to 25,000 remain in the wild. Their range has contracted into scattered regions separated by farms, roads, settlements, and fences. Each surviving population occupies a smaller piece of the landscape than its ancestors once knew, making movement between groups increasingly difficult and reducing opportunities for healthy genetic exchange. Tigers tell a similar story across an even broader geography. They once roamed from what is now Turkey across much of Asia to the Russian Far East. Forests, grasslands, and wetlands supported several distinct populations, connected across enormous distances. Today, those continuous habitats have become isolated reserves surrounded by human development. Between roughly 3,500 and 5,000 wild tigers remain, divided into populations that often rely upon careful conservation management to maintain long-term viability. Cheetahs carry an additional burden written into their genes. Fewer than 7,000 survive worldwide, and their genetic diversity was already greatly reduced by a severe population bottleneck approximately 10,000 to 12,000 years ago. That ancient decline occurred during the same broad period when many Ice Age mammals disappeared. Cheetahs endured where Smilodon did not, although the survival margin appears to have been exceptionally narrow. Modern studies continue to detect the lasting signature of that ancient contraction within their genetic makeup. Across these different species, familiar pressures converge. Habitat shrinks as human activity expands. Large grazing animals decline through hunting and landscape alteration. Encounters between people and predators become more frequent, often ending poorly for the cats. None of these influences acts entirely alone. Each reinforces the others until the combined burden becomes heavier than any individual challenge. The importance of prey remains especially striking. In places where antelope, deer, or other hoofed mammals become scarce, large cat populations decline even when people rarely kill the predators directly. Food webs unravel from their foundation upward. The disappearance of herbivores ripples through every hunting species that depends upon them, echoing patterns reconstructed from the closing centuries of the Ice Age. Flexibility also continues to shape survival. Leopards consume an unusually broad range of prey and tolerate forests, mountains, grasslands, and even landscapes bordering towns. Lions and cheetahs occupy narrower ecological roles, making them more vulnerable when those conditions deteriorate. The same evolutionary balance between specialization and adaptability remains visible across living ecosystems. Small, isolated populations introduce another challenge. As groups become separated, genetic diversity gradually declines, reducing resilience against disease and environmental change. Conservation biologists recognize this process in endangered cats today because fossil evidence suggests comparable fragmentation likely affected Smilodon during its final centuries. The paths are not identical, and history never repeats with perfect symmetry. Even so, the living descendants of other feline branches continue walking across landscapes where the balance between abundance and disappearance can shift within the span of a human lifetime, leaving the fossil record to begin its patient work once again. Some absences leave space that can eventually be filled. Others become permanent features of the world itself. Smilodon's disappearance belongs to the second kind. The passage of time can soften the traces left in rock and soil, yet it cannot rebuild the particular evolutionary path that produced this predator. Once that path ended, an entire collection of biological possibilities vanished with it. Evolutionary biologists describe this idea as irreplaceability. Every species represents a distinct solution to the challenge of survival, assembled through countless generations of natural selection. Different animals may arrive at similar adaptations through convergent evolution, yet the complete combination of anatomy, behavior, ecology, and history embodied by one extinct species cannot be recreated. Even if another predator were someday to evolve elongated canine teeth, it would emerge within a different ecosystem, from different ancestors, under different environmental pressures. The original design remains permanently beyond recovery. What disappeared with Smilodon reached far beyond an individual animal. More than 23 million years of refinement had shaped one of the most sophisticated hunting systems ever produced by a land mammal. Every modification of the forelimbs, shoulders, neck, skull, and canine teeth formed part of a tightly integrated design. Each generation inherited slight improvements from the last until the entire predator became exceptionally effective within the world that had shaped it. Evidence preserved at La Brea also hints at another loss that cannot be measured directly. Numerous skeletons display severe injuries that had healed long before death, suggesting some individuals survived periods when hunting alone would have been nearly impossible. If these fossils truly reflect cooperative living, then Smilodon possessed social bonds involving shared care and perhaps coordinated hunting. Bones can suggest such relationships, yet they cannot preserve every interaction, every learned behavior, or every bond between companions. Much of that social world disappeared without leaving a complete record. Its ecological role also ended. Smilodon helped regulate populations of large grazing mammals across broad regions of the Americas. Predators influence which animals thrive, where herds travel, and how vegetation responds to changing patterns of grazing. Removing one dominant hunter alters those relationships in ways that continue long after the predator itself has vanished. Ecologists sometimes describe this lasting influence as ecological memory. Modern forests and grasslands across North America still carry subtle signatures left by ecosystems that once included giant herbivores and the predators that pursued them approximately 10,000 years ago. The loss unfolded across many layers at once. A distinctive body plan disappeared. Complex behaviors faded beyond observation, ecological relationships unraveled. An evolutionary experiment extending across geological time reached its conclusion. None of those layers can be separated from the others because each depended upon the rest. Many forms of damage can eventually be reversed. Rivers return after drought. Burned forests grow again. Species maintained through captive breeding programs sometimes reclaim parts of their former range. Extinction closes a different kind of door. Once an entire lineage has vanished, no remaining population exists from which renewal can begin. Recognizing that permanence carries a particular weight, it does not ask for sorrow in the human sense. It offers something quieter than emotion, an awareness that the history of life contains chapters whose final pages cannot be rewritten, no matter how completely we come to understand the story they tell. A fossil can appear complete long before it has surrendered everything it knows. For much of the past century, a Smilodon skeleton was valued mainly for its shape, its age, and the clues visible to the human eye. Today, each specimen offers another layer of evidence. Advances in chemistry, imaging, and dating have transformed familiar bones into detailed archives, allowing scientists to examine the closing centuries of the species with remarkable precision. One of the greatest advances has come through improved radiocarbon dating of the asphalt preserved fossils at La Brea. The sticky petroleum that trapped the animals also preserved collagen within many of their bones. Researchers developed specialized methods to separate the ancient biological material from the surrounding asphalt contamination, making accurate dating possible. The methodology refined for the recent studies has allowed scientists to identify the last radiocarbon dated individuals of several species with a level of precision that earlier generations could not achieve. Instead of broad spans lasting thousands of years, many disappearances can now be constrained to windows measured in centuries. Chemical analysis adds another dimension to this chronology. Isotopes preserved within bone collagen record the foods consumed during an animal's lifetime. By comparing these chemical signatures among Smilodon individuals from different ages, researchers can determine whether hunting patterns changed as ecosystems transformed. Shifts in isotope values may reveal alterations in preferred prey, movement across changing landscapes, or adjustments forced by declining herbivore populations. These measurements preserve dietary history in ways no skeleton alone could reveal. The bones themselves contain an equally valuable record of health. Thousands of Smilodon fossils recovered from La Brea include healed fractures, arthritic joints, worn teeth, and developmental abnormalities. Examined across many generations, these pathologies provide a portrait of population condition through time. Scientists can compare injury frequencies and skeletal disorders from older deposits with those from the final populations, searching for evidence of increasing stress as environmental conditions deteriorated. The surrounding sediments preserve the landscape alongside the animals. Thin layers of pollen reveal changing plant communities, while charcoal fragments document the history of wildfire through successive centuries. Together, they record open grasslands gradually giving way to expanding chaparral as the regional climate shifted. Because these environmental layers surround the fossil deposits, they provide an independent timeline against which the disappearance of each species can be compared with exceptional resolution. The famous carnivore trap also became an unexpected recorder of ecological decline. Distressed herbivores struggling within the asphalt attracted predators searching for rare feeding opportunities. As large prey became less abundant across the surrounding landscape, these natural traps may have become increasingly important gathering places for hunters. Many of the final Smilodon individuals likely approach the trapped animals, seeking one more successful meal, only to become preserved beside them for thousands of years. New discoveries continue to extend this story. During construction associated with underground infrastructure near La Brea, paleontologists uncovered 16 major fossil deposits through an excavation effort known as Project 23. Those deposits remain under careful study, yielding additional specimens and environmental evidence that continue to refine the chronology of the Ice Age ecosystem. The work resembles detective investigation conducted across immense spans of time. Every tooth, pollen grain, charcoal fragment, and collagen sample contributes another sentence to a narrative assembled from its ending backward. Researchers also continue attempting to recover ancient genetic material from asphalt preserved fossils. The chemistry differs greatly from frozen permafrost, making extraction exceptionally difficult, yet success could reveal the genetic diversity of Smilodon's last populations with unprecedented clarity, bringing the final chapter into even sharper focus. There is a temptation to measure the past by its ending, as though the final page defines everything written before it. Smilodon invites a different perspective. Its disappearance is undeniable, yet the span of life that preceded it stretches across approximately 2.5 million years. During that immense interval, it occupied ecosystems across much of the Americas, refined one of the most specialized hunting systems ever produced by evolution, and persisted through changing climates that would have erased countless less capable predators. Its story presents a deeper question about specialization itself. Evolution rewards mastery whenever the surrounding world remains sufficiently consistent. Every improvement that increases efficiency also strengthens dependence upon the conditions that made the improvement valuable. Longer canine teeth, stronger forelimbs, carefully coordinated killing mechanics, and behavior suited to enormous prey formed a system of remarkable effectiveness. Those refinements also narrowed the range of circumstances under which the same system could succeed. Mastery and vulnerability were never separate outcomes. They were different expressions of the same evolutionary path, revealed only across different spans of time. This perspective changes the meaning of extinction. Smilodon did not disappear because evolution had somehow failed to perfect it. Evolution had accomplished exactly what natural selection favored for millions of years. The difficulty emerged only after the surrounding world began changing more rapidly than biological adaptation could follow. The qualities that once provided overwhelming advantage remained exactly as they had been. The landscape around those qualities shifted until they no longer aligned with reality. The challenge extended beyond anatomy. No animal possesses a way of recognizing that a familiar decline marks the beginning of a permanent transformation rather than another temporary hardship. A season of scarce prey had likely occurred many times before. Populations recovered, herds expanded, and predators continued their lives. During the closing centuries of the late Ice Age, the same signals concealed a fundamentally different future. There was no biological mechanism capable of recognizing that the prey base itself was entering lasting collapse. Evolution carries no instrument that predicts conditions generations before they arrive. The pattern reaches beyond prehistory without requiring direct comparison between human societies and Ice Age predators. Modern civilization also builds extraordinary systems through specialization. Industries refine particular technologies. Agriculture develops crops suited to specific climates. Individuals devote years to mastering narrow fields of knowledge. Such specialization produces remarkable achievements while depending upon conditions that remain reasonably stable. Flexibility and mastery often exist in delicate balance, each offering strengths that become visible under different circumstances. Seen across geological time, Smilodon's existence resembles neither triumph nor failure in the ordinary sense. A lineage that flourished across continents for approximately 2.5 million years achieved extraordinary evolutionary success. Fossils preserving healed injuries even suggest social lives in which injured companions survived with assistance from others, revealing complexity beyond hunting alone. Nothing about that history resembles a failed experiment. Its conclusion reflects the arrival of environmental change, unfolding more rapidly than natural selection could redesign a highly specialized predator. Perhaps that leaves a different understanding of success itself. Human lives often measure achievement across decades. Evolution measures persistence across thousands or millions of generations. A lineage may thrive beyond imagination before eventually reaching its conclusion, just as mountains rise and wear away without diminishing the immensity of their existence. Smilodon reminds us that endings do not erase greatness. They reveal that even the most refined creations of evolution remain participants in a changing world whose pace, at rare moments, exceeds every living creature's ability to follow. A collection of fossil bones can appear to belong entirely to another age, separated from the present by thousands of generations. The researchers, working at Brea, describe something different. In the peer-reviewed study published during 2023, they concluded that the patterns emerging from the final centuries of the Ice Age present an ominous parallel to challenges humanity faces on a planetary scale today. Their statement is offered as scientific interpretation grounded in evidence gathered from the fossil record itself. The comparison rests upon mechanism rather than symbolism. The evidence assembled from radiocarbon dating, pollen preserved within sediment, fossil distributions, and ecological reconstruction points toward a combination of climate-driven habitat transformation and expanding human influence. Together, they pushed ecosystems across a threshold beyond which recovery no longer followed familiar patterns. Habitat shifted, prey communities unraveled, specialist predators lost their foundation, and extinction accelerated. Those interacting forces formed the operating model reconstructed for the closing stages of the late Pleistocene, and the same combination continues to shape ecosystems across the modern world. Current estimates suggest species are disappearing at roughly 100 to 1,000 times the long-term background rate inferred from the geological record. The overall magnitude has not yet matched the great extinction events preserved in Earth's history, yet the speed has drawn increasing scientific attention. Rapid environmental alteration, habitat fragmentation, and human pressure are compressing ecological change into intervals far shorter than those that once allowed many species to adapt through ordinary evolutionary processes. The pattern within living predators echoes what the fossils reveal. Large carnivores requiring extensive territories and dependable populations of sizable prey often decline first as landscapes become divided and food webs weaken. Animals with broader diets and greater flexibility usually persist longer. Smaller predators, capable of feeding upon rodents, birds, insects, fruit, carrion, or many combinations of available resources, continue finding opportunities after specialists begin disappearing. The same ecological contrast can be traced backward through the La Brea record, where highly specialized hunters faded while adaptable survivors remained. Perhaps the most striking difference between the closing ice age and the present lies in knowledge itself. Smilodon's disappearance is no longer an unsolved mystery. Scientists have reconstructed prey decline, environmental transformation, increasing fire activity, shrinking habitat, ecological specialization, and indirect human influence with remarkable precision. The broad outline of the process has become increasingly clear through decades of accumulating evidence. The fossils no longer leave us wondering what happened. They instead demonstrate how interacting pressures can combine until an ecosystem crosses a point beyond which familiar stability cannot return. That understanding gives new meaning to the idea of an endling, the final individual representing an entire lineage. During 2018, the last male northern white rhinoceros died after years of intensive protection and worldwide attention. His passing unfolded before cameras rather than inside natural asphalt. His name, his history, and even the date of his death became part of the scientific record. The final member of a lineage no longer exists only in deep time. It can stand before us in the present, fully documented. La Brea therefore preserves more than extinct animals. It preserves a sequence of ecological decisions written into stone, pollen, enamel, and bone. The researchers uncovering those layers continue reading them with increasing precision, discovering that the record does not merely explain one vanished predator. It demonstrates how ecosystems respond when multiple pressures converge faster than living communities can reorganize. That message belongs equally to the Ice Age and to the living world surrounding us today. The story has not reached its final sentence, even though its central character disappeared thousands of years ago. Every season of excavation at La Brea offers another opportunity for Smilodon to speak through the traces it left behind. The animal itself cannot return, yet the evidence surrounding its life continues expanding as researchers uncover specimens that remained buried, unopened, and unread until the present day. The collections housed at the Page Museum stand among the richest fossil archives on Earth. More than 3.5 million specimens have been recovered from the asphalt deposits, representing plants, insects, birds, reptiles, and mammals preserved together within the same extraordinary record. Thousands of those fossils are still being cataloged, prepared, and studied. Every newly identified bone, tooth, or fragment has the potential to refine what scientists understand about the ecosystem Smilodon inhabited and the pressures that eventually overwhelmed it. One of the largest sources of new material arrived unexpectedly through Project 23. During nearby construction, workers uncovered 16 substantial fossil deposits preserved beneath the surrounding ground. Each deposit was removed inside massive wooden containers so that excavation could continue under carefully controlled museum conditions. Years later, those deposits are still yielding discoveries. New individuals emerge from sediment that had remained untouched since the late Pleistocene, adding fresh information to a record that many once assumed had already revealed most of its secrets. Technology has expanded alongside the fossil collection itself. Many Smilodon specimens entered museum storage decades before modern imaging techniques became available. Today, computed tomography scanning allows researchers to examine internal bone structures without damaging irreplaceable fossils. Hidden fractures, patterns of bone growth, developmental abnormalities, and healed injuries can now be recognized in specimens that appeared fully understood when they were first cataloged. The same skeleton can therefore contribute entirely new evidence despite resting in museum collections for generations. Another frontier remains even more ambitious: Scientists continue attempting to recover ancient genetic material from asphalt preserved specimens. The chemistry of natural asphalt creates challenges very different from those encountered in frozen environments, making successful extraction exceptionally difficult. Even so, each improvement in laboratory methods renews the possibility that fragments of Smilodon's genetic history may eventually be recovered. Such evidence could reveal how much genetic diversity survived within the final populations and whether that diversity diminished as extinction approached. Recent research has already reshaped long accepted ideas. Studies published within the past 5 years have refined estimates for extinction timing, strengthened evidence supporting social behavior, and identified increasing dietary stress during the closing stages of Smilodon's existence. Each investigation adds another layer of resolution without overturning the broader picture. Instead, the portrait becomes sharper, replacing uncertainty with carefully measured detail gathered from fossils that continue yielding information long after their discovery. This makes the study of Smilodon unlike the study of any living species. A biologist observing modern animals may witness new behaviors unfolding directly in the field. Paleontologists work through a different conversation, assembling lives from bones, enamel, pollen, collagen, and sediment. Every conclusion emerges through patient forensic reconstruction, each specimen contributing another sentence to a history written from physical evidence alone. The remarkable consequence is that extinction has not ended discovery. Smilodon continues revealing itself through the record it left behind, one carefully prepared fossil after another. Each new finding deepens the understanding of how such an accomplished predator lived, adapted, struggled, and finally disappeared, leaving behind evidence that grows richer even as the distance from its world continues to widen. Some spans of time refuse to fit comfortably inside the human imagination. They can be measured, written, compared, and spoken aloud, yet they continue slipping beyond ordinary experience. Smilodon existed for 2.5 million years. The statement is scientifically straightforward. Living with the meaning behind it is something entirely different. That duration extends beyond the entire existence of the genus Homo. It reaches farther into the past than the earliest widely accepted stone tools by a considerable margin. Entire human lineages appeared, changed, and disappeared while generations of Smilodon continued hunting across the landscapes of the Americas. The predator's story unfolded through cycles of changing climates that no individual could perceive, yet each generation inherited a world shaped by countless lives that came before. Human civilization occupies only a slender fraction of that interval. Agriculture, writing, cities, kingdoms, empires, scientific discovery, and every recorded chapter of history together span roughly 10,000 years. Smilodon endured for approximately 250 times that length of time. Every library, monument, and surviving document belongs to a period that would occupy only a narrow portion near the end of the predator's existence. The comparison does not diminish humanity. It enlarges the scale on which evolution unfolds. The broader saber-toothed lineage stretches even farther. For approximately 23 million years, it refined a distinctive approach to predation, generation after generation, across changing continents and shifting climates. If that entire history were compressed into a single day, the complete record of human civilization would appear only during the final few seconds before midnight. The comparison is imperfect, yet it offers a glimpse of the extraordinary depth contained within a lineage that has now completely vanished. Perhaps this is why the word extinct feels strangely small. It is accurate, precise, and scientifically necessary. At the same time, It compresses 2.5 million years of existence into a single past tense description. One word stands where millions of seasons once unfolded, where countless hunts succeeded or failed, where cubs matured, adults aged, injuries healed, and populations adapted as the living world continued changing around them. Other endings leave pathways back. A drought may give way to rain. A forest can recover over centuries. Even a language may sometimes be revived when enough knowledge survives. An extinct lineage belongs to a different category entirely. Once the final member disappears, the evolutionary journey that produced it also ends. The branch no longer extends into the future, regardless of how completely its history has been preserved. That history remains beneath the streets of Los Angeles. Thousands of Smilodon individuals still rest within natural asphalt deposits, each representing an entire lifetime filled with choices, encounters, hardships, and survival. Scientists recover those bones piece by piece, prepare them with extraordinary care, catalog them, and compare them with every new discovery. Each specimen adds another fragment to a record that has never stopped expanding. The animal itself will never walk again, yet the evidence continues speaking with increasing clarity. Every excavation, every improved analytical method, and every careful comparison brings another detail into focus. The distance between the present and the Ice Age grows greater with each passing year, while the understanding carried by those preserved bones becomes richer, allowing an existence measured across millions of years to remain part of the living story of Earth. 10,000 years ago, the world was changing in ways no living creature could measure. Grasslands were giving way to new plant communities. Great herds no longer crossed familiar routes in the same abundance. Smoke drifted across seasons that had once been more predictable. Somewhere within that changing continent, the last Smilodon lived through its final days. We do not know the place. We do not know the exact year. We do not know whether another of its kind remained nearby. The evidence gathered across decades now allows much of the larger story to stand with unusual clarity. A predator refined through approximately 2.5 million years of its own existence, and through roughly 23 million years of saber-toothed lineage history, reached extraordinary effectiveness within the world that shaped it. Then that world shifted. Temperatures rose, vegetation changed, large prey became less dependable. Human expansion introduced pressures unlike any the lineage had previously encountered. None of those forces acted alone. Together, they formed a convergence that evolution had never prepared this hunter to meet. Its ending almost certainly lacked the grandeur that imagination often prefers. There was no final battle marking the close of the lineage. More likely, populations became separated from one another as suitable habitat shrank. Hunting succeeded less often. Old injuries carried greater consequences when food became uncertain. Fewer cubs survived to adulthood. Genetic diversity narrowed as isolated groups lost contact across increasing distances. One population disappeared, then another, until the final survivors occupied landscapes that no longer resembled those in which their remarkable adaptations had first flourished. Natural asphalt at La Brea preserves thousands of reminders of that long history. Approximately 2,000 individual Smilodon skeletons and partial skeletons have been recovered during more than a century of excavation. Each discovery joins a growing archive assembled by researchers who continue preparing fossils, comparing specimens, refining dates, and testing ideas with methods unavailable to earlier generations. The collection has never become a finished story. Every new analysis adds another sentence to a record written across deep time, across those bones, the chemical traces preserved within them, the injuries that healed, the teeth that wore down, and the sediment that surrounded each specimen. One message appears again and again. Something can endure for spans of time that exceed ordinary imagination. It can become woven so completely into an ecosystem that permanence seems almost inevitable. Even then, permanence remains an illusion measured only from the perspective of a brief human lifetime. The animal itself no longer walks beneath open skies. Its lineage extends no farther into the future. What remains are the physical traces of lives once fully lived, preserved beneath a modern city where streets, buildings, and passing traffic now occupy ground that once drew Ice Age animals toward pools of natural asphalt. Those bones continue to emerge from the earth, carrying details that no written history could preserve. They speak through careful measurement, patient comparison, and steady observation. Their account asks for nothing beyond attention. Smilodon was real. Its existence stretched across a depth of time that almost escapes comprehension. Its disappearance was gradual, permanent, and complete. The record remains, resting within the tar, still offering its testimony to anyone willing to listen across the immense distance between its world and ours. Smilodon is gone. That fact has remained unchanged for approximately 10,000 years, yet extinction did not erase everything the animal left behind. Alongside the bones preserved within natural asphalt, another inheritance continued taking shape. Each generation of researchers added another layer of understanding until the predator became one of the most completely studied extinct hunters ever known. The discoveries made through the fossils at La Brea have transformed far more than the biography of a single species. They helped establish new ways of investigating extinction itself. Improved radiocarbon dating techniques, developed for asphalt-preserved fossils, have made it possible to determine the final appearance of Ice Age animals with a level of precision that earlier generations could scarcely imagine. Those methods now contribute to research extending well beyond one fossil deposit, offering scientists better tools for reconstructing the timing of biological change in many different environments. As the evidence accumulated, the meaning of Smilodon's disappearance also became more practical. Wildlife biologists studying living predators now recognize familiar patterns within the fossil record. The collapse of large prey populations, increasing ecological specialization, fragmentation of habitat, and indirect human influence combine into a framework that guides conservation planning today. The story preserved in the bones is therefore more than a record of one vanished hunter. It has become a reference for understanding how large carnivores respond when the ecological foundations supporting them begin to disappear. California formally recognized that importance during 1973 by designating Smilodon as the official state fossil. The choice acknowledged something larger than scientific interest. This predator belongs to the identity of the region, even though no living individual has walked there for thousands of years. Modern neighborhoods, highways, and museums occupy landscapes that once formed part of its range, allowing the memory of the animal to remain connected to the place where so much of its history has been uncovered. Its presence extends beyond scientific collections. Smilodon has become one of the most recognizable prehistoric animals on Earth. Museum galleries, documentary films, carefully researched illustrations, sculptures, and educational exhibits continue introducing new generations to the Ice Age world. The familiar profile of the elongated canine teeth has become a symbol reaching far beyond paleontology. carrying with it an enduring curiosity about the ecosystems that shaped such an extraordinary predator. There is another perspective that lends unexpected closeness to the story. Smilodon endured for approximately 2.5 million years. The genus Homo has existed for roughly a similar span, emerging during the same broad chapter of Earth's history. In that sense, our lineage and its lineage belong to the same Pleistocene world, responding to many of the same climatic rhythms, even while following very different evolutionary paths. The portrait available today would have been unimaginable only 50 years ago. Evidence for cooperative social behavior, refined timelines for extinction, detailed studies of dietary stress, recognition of fire driven ecological transformation, precise endling dates, and clearer links between prey decline and predator disappearance have all emerged through continuing research. Every advance has sharpened the image without diminishing its wonder. Bones endure longer than flesh, yet knowledge can outlast them both. Each fossil prepared, each measurement repeated, and each new question asked allows Smilodon to remain part of the living conversation about life on Earth. Its footsteps have long since faded, but the understanding they inspired continues moving forward, carried by curiosity instead of survival. 10,000 years ago, the world was changing in ways no living creature could measure. Across western North America, familiar hunting grounds were becoming different places. Grasslands retreated, great herds grew fewer, fire returned often enough to reshape entire landscapes. Somewhere within that changing world, the final Smilodon drew its last breath. No witness remained to record the place. No season marked the moment. Time carried it forward without announcement, leaving only the traces that settled into the asphalt below. Those traces still rest beneath one of the largest cities on Earth. Streets, homes, offices, and gardens now surround the deposits at La Brea, while thousands of fossil bones remain preserved below the surface. They continue to emerge through careful excavation, one specimen after another, cleaned with patient hands, cataloged with growing precision, and compared against discoveries made decades apart. Every recovered tooth, vertebra, rib, and limb becomes another line in a record that has never truly stopped expanding. The story those fossils preserve stretches across approximately 2.5 million years. That span exceeds the age of the entire genus Homo. It reaches far beyond the full history of farming, writing, cities, kingdoms, navigation, industry, and every chapter of recorded civilization combined. Human technological development occupies only the smallest fraction of the interval during which Smilodon lived, hunted, raised young, recovered from injuries, and continued passing its inheritance from one generation to the next. The bones also preserve something that earlier generations could never have reconstructed. They reveal how extinction unfolded with remarkable clarity. Improved dating methods, chemical studies of diet, analyses of healed injuries, environmental records preserved in sediment, and careful comparison across thousands of individuals have shown that disappearance followed a sequence rather than a single catastrophe. Shrinking prey populations, changing habitats, increasing ecological pressure, and the arrival of human hunters combined into conditions that exceeded the capacity of even a remarkably successful predator to adapt within evolutionary time. That understanding now stands as one of the clearest scientific portraits of extinction ever assembled. Knowledge like this possesses an unusual permanence. The animals themselves cannot return, yet what they left behind continues yielding information with every new technique developed by paleontologists. Instruments unavailable a generation ago now reveal details concealed within bones that have rested underground since the end of the Ice Age. Questions once thought impossible to answer continue finding careful replies, allowing the record to grow sharper without altering the final outcome it describes. Perhaps that is what makes La Brea such an uncommon place. It preserves absence with extraordinary detail. Thousands of complete lives remain present as evidence, while the living population they once formed has vanished beyond recovery. The fossils cannot restore the sound of a hunt or the movement of a family group across an open plain. They preserve something different, the enduring ability to understand what truly happened. The record remains beneath the city, the bones remain within the asphalt, and the story remains open to deeper understanding. While the animal itself remains one of Earth's most extraordinary lives, carried now only by time, memory, and the patient testimony of what it left behind.